Good afternoon, Algebra 2 students. We are talking today about the natural base e. E is an irrational number, just like pi. We know pi to be about 3.14. E has a value also. Can you find e on your calculator? It's the second function of the natural log. If you type in second e, you're going to want to put in the exponent that you're looking for. So we're going to start with e to the first. So grab your calculators, type in e to the first, and you should come up with a number that is about 2.71828 and so on. As I stated, it's an irrational number, so it's non-terminating, non-repeating. We usually abbreviate it to be about 2.718. The inverse function of e is the natural log, which is abbreviated ln. In other words, if you type in the natural log of 2.71828, you should find that that is pretty much equal to 1. Because e and the natural log are inverses, they undo each other. We're going to do several things with the base e. The first thing we're going to do is graph it. It's an exponential function, so it should look like an exponential growth or an exponential decay function. We're going to start with simply e to the x. I'm going to input the numbers from -2 to +2. You can type these in with me and make sure that you get the same values. When I type in e to the power of -2, I get about 0.14. E to the power of -1, I get about 0.37. Anything to the power of 0 is 1. E to the first is about 2.72. And e to the second is about 7.39. If I graph those data values, 0.14, 0.37, 1, 2.7, and 7, I do get that exponential curve. It's an exponential growth function. Its domain is all real, and its range would be y is greater than 0. This function can be translated just like all of the other functions that we've done. How would you expect this equation to be translated? I hope you said up 3 because there's a +3 at the end. If I inputted these numbers into my calculator, I should indeed get about 3.14, 3.37, 4, 5.72, and 10.39. So I should take that entire red graph and shift it up 3. Just going to sketch that. You'll have graph paper to work on yours, so you can do a more exact graph. Okay, so we should be able to graph exponential functions. We should also be able to simplify them. Remember, natural log is base e. If I write common log of 7, remember you are going to know that if there's no number written right here, that's base 10. Now if I write natural log, you're going to know that if there's nothing written here, that's base e, because natural log and e automatically go together. So this first function that they wrote, natural log of e to the 7th, really is natural log base e of e to the 7th. We learned in a previous lesson that when these bases are the same, they cancel each other out. So if I simplify, this should just equal 7. Same process here. I can write in the base if I so choose. These cancel. So this should just be equal to -2x. It works when e is the base and the natural log is the exponent also. I can think of this as a base e here. These cancel, and this is just equal to x minus 2. The last one on the page is the only thing we have to do a little work for. Remember when this 3 is sitting out front that's actually an exponent. I should rewrite this as e to the power of natural log x cubed before I simplify. Then my base e's will cancel, and this should just be equal to x cubed. One of the most common things that base E is used for is interest, compound interest. We've looked at the compound interest formula before. Let me remind you how it looks like. Recall from previous instruction that Y is the final amount, A is the initial amount, R is the rate, T is the time, and if we're compounding, N is the number of times per year that we're compounding. Remember, if we're compounding quarterly, N is 4. If we're compounding monthly, N is 12, and so on. When I switch to compounding continuously, that means that they're putting my interest in my account at every second, faster than every second, just continuously. And E is the base for our continuous compounding formula. Continuous compounding looks like this, where Y is the final amount, P is the initial amount, R is the rate, and T is the time. Let's see how that changes our final amount if we compound interest in different ways. So I'm going to start with the equation of $10,000 at 6% for 20 years. I want to begin by compounding it annually. Annually, my equation would look like this. Y equals 10,000, 1 plus 6%. If I'm only compounding it annually, then I would divide by 1, so I didn't write that. And 1 times 20 is 20. Type this in your calculator with me. Make sure we get the same answer here. So 10,000 times, use your parentheses, 1 plus 0.06 to the power of 20. And I came up with $32,071.35. Monthly. How does this equation change if we compound it monthly? Well, if we're compounding it monthly, we have to divide the interest and multiply the time by 12 because there are 12 months in a year. So I'm going to put 1 plus 0.06 divided by 12, and 12 times 20 is 240. Use your parentheses, type with me, 10,000 times 1 plus 0.06 divided by 12 to the power of 240. And you'll see that we earned a little more money compounding monthly than if we compounded annually. Now at the end of 20 years, we have $33,102.04. Let's change that equation to compounding daily. Now I have 10,000, 1 plus 0.06. There are 365 days in a year, so we have to divide by 365. And then we have to take 365 times 20, which is 7,300. If we enter this equation into our calculator, type with me, I get a total amount now of $33,197.90. Finally, we're going to compound it continuously. So I'm going to use our new formula. We still have an initial amount of 10,000. Then I have e to the power of rate times time. So on my calculator, I'm going to type 0.06 times 20, and I would have an exponent of 1.2. Okay, so now I want to type 10,000 times e to the power of 1.2. You'll notice that this just went up a few dollars, but it does give us a little bit higher amount than if we compound it daily. You should get $33,201.17. You'll want to write down the compounded continuously formula in your notes. You will be using it, so if you need to pause the recording to take notes, do so at any time. The other item that E is used for is in our half-life formula. You've probably used a half-life formula in science class before. The half-life of a substance is the time it takes for half the substance to break down or convert to another substance during the process of decay. Natural decay is modeled by the function below. where n of t is the final amount, n sub 0 is the initial amount, e is our exponential base, k is a decay constant, and t is the time. Let's see if we can use that formula. Plutonium 239 has a half-life of 24,110 years. How long does it take for a 1 gram sample to decay to 0.1 grams? Okay, I'm going to write the formula. Remember, final amount, initial amount, E negative KT. Before we can use the formula, we have to find the decay constant, the K value. Anytime you want to find the decay constant, you're just going to put in 1 for the starting amount and 1/2 for the ending amount, because it says it takes 24,110 years to get half as much. So if we start with 1, we end with 1/2. So 1 times E negative K, and the time it takes for it to get half as much is 24,110 years. Okay, I could divide by this 1, but it doesn't do anything for me, so actually I'm just going to erase that 1 and eliminate it. Now I need to solve. I need to solve for an exponent. To solve for an exponent, we use a log. If we are using base e, we want to use a natural log. If I change this to my log equation, it should look like this. Natural log base e, which I wouldn't have to write because natural log is always base e, of 1/2 equals negative k times 24,110. Pick up your calculators and type the natural log of 1/2. You should get negative 0.693 and so on. Then I'm going to divide that by negative 24,110. Decay constants are always really small. As a matter of fact, it showed up in scientific notation on my calculator. But if I move the decimal over, I get a constant of 0.0000287. If you did not get that, please check again. Now we're going to find the time it takes for 1 gram to end up at 0.1 grams. So filling in my amounts, my final amount is 0.1. My initial amount is 1. I now know my constant. My constant is 0.0000287, and the time is what I'm looking for. Again, this 1 doesn't do anything for me. If this was a number other than 1, I'd divide by it, but since it's 1, I'm going to just eliminate it. And now again, to solve for an exponent, we're going to switch it to a log. So we're going to switch this to natural log of 0.1. I could write the base e, but I don't have to, equals negative 0.0000287t. On your calculator, type the natural log of 0.1 and then divide that by negative 0.0000287. We should find out that it's going to take about 80,229 years for our plutonium to decay to 1/10 of its original amount. The last thing I want to show you today is solving natural log equations. We do this just like we solve any other type of equation. If we want to solve a log, we change it to an exponent. If we want to solve an exponent, we change it to a log. On the first problem, I'm going to condense that first. Let me remind you, when you're condensing, this 2 is an exponent. So that's the natural log of 3 squared. I'll do this one step at a time. Condensing that right-hand side, remember plus means to multiply, so that's the natural log of 9x equals 4. Changing it to an exponent, well, remember this time we have base e right here. So e to the 4th equals 9x. On my calculator, I'm going to type e to the power of 4. And then I'm going to divide that by 9. And I'm going to get that x is about 6.07. Solving the second problem, I have an e, so I'm going to change it to a log. Since it's base e, I'm going to use natural log. This one would be natural log base e if we want to put it there, but we don't have to. So natural log of 12 equals 3x. Use your calculator to type natural log of 12 and then divide that by 3, and you should get an x value of about 0.83. And finally, this one looks a little different. We have a base e here and a base e here, so those actually cancel. This equation becomes simply 2x equals 10, so x equals 5. The examples I've shown you are similar to the examples on your assignment for today and the worksheet for tomorrow. So if you need to replay this recording to see another example again, please feel free to do so. Good luck with your STEM activity in Eureka and have a good weekend. Bye.